Okay, Bismillah Rahman Rahim. Now, today is lecture number 12 of the course Hydraulics, and we will continue our discussion with similitude. And then, in the next part of the lecture, we will study about dimensional analysis. So, in the previous lecture, we studied about similitude or similarity. So similarity means similarity between the model and the prototype. So in order that similarity exists between the model and the prototype, then we can transfer the results from the model to the prototype. Means that we can predict the performance of the prototype by conducting tests on scaled models. So in order to do that, we have to ensure that there is similarity between the model and the prototype. So we studied about three types of similarities. So geometric similarity, kinematic similarity, and dynamic similarity. So we studied that if dynamic similarity exists between the model and the prototype, this is in addition to the geometric and kinematic similarity. And dynamic similarity exists when the forces that are acting in the model and the prototype, they are the same. Clear? So the same means that we discuss that the ratio of the forces, the inertia force by gravity force or viscous force or other forces, we defined that these actually form the dimensionless numbers. So if, for example, we studied about the Reynolds number and the Froude number in the previous lecture. So if they are the same in both the model and the prototype, then we can say that there is dynamic similarity between the two. So we continue our discussion with the Froude number. So the Froude number, we already know that it is the ratio of inertia forces to the gravity forces, and it can be written in this form. Because you see these are numbers, because these are the ratio of two similar quantities. So the unit cancel out, so we do not worry about the units. Reynolds number, ratio of forces, inertia force by viscous force. Similarly, this Froude number, which we have studied in detail in open channel hydraulics chapter, so it is the ratio of inertia force by gravity force. Now it can be written in this form. We already discussed in the previous lecture that what could be the expressions for these forces. So this is equal to V square divided by GL, where L is the characteristic length. Now this is also the possible form. The Froude number is equal to this. That's why it is written in your textbook that although this is sometimes defined as the Froude number, it is more common to use the square root. Means that you take the square root of this quantity here. You take the square root of this. Clear? So we can commonly express this in this form here. This is what we have used analyzing the open channel flow problems. V divided by square root of GL. Now, as I said before that we have these dimensionless numbers, the Reynolds number, the Froude number, and we will study some other numbers that are commonly found and used in fluid mechanics. But there can be so many numbers we can define. Since because it is the ratio of two forces, so there can be many forces. So that's why, as I said before, if we want to ensure that there is dynamic similarity between the model and the prototype, First, we have to identify that what forces are significant in this specific fluid mechanics problem. This is important because, for example, you see these are the cases where the gravity and inertia forces, these are important. For example, wave action set up by a ship, the flow of water in open channels, the forces of stream on a bridge pier spillways, and the flow of jet from an orifice. Just like you studied and conducted even experiment in fluid mechanics 2 lab, orifice and jet apparatus. Now in this case, you see that in these examples, the gravity and inertia forces are significant. So that's why when we do the analysis of these fluid phenomena, we have to consider the Froude number for dynamic similarity. If instead you consider the Reynolds number for dynamic similarity, so then in that case, results will not be accurate. So that's why the basic understanding or knowledge of the fluid mechanics is very important before we apply these concepts. So remember, you must understand very well the phenomena in order to analyze the problem, because there are so many dimensionless number. If you pick the wrong one and try to analyze the problem, the results will not be realistic. For example, you see here there is a velocity present here in this case. Now this same velocity is also present when you consider the Reynolds number. So if we want to say that, okay, the velocity in the model is this much, what will be the corresponding velocity in the prototype? So if you calculate from Froude number and you fully understand that in that case the Froude number needs to be considered, the results will be realistic. But for example, if you apply the Reynolds number, there V is also present, and you want to calculate the velocity in the prototype, then in that case you may not get the realistic results. So that's why understanding of the basics in order to use these concepts, that is very important. Not only in this similitude, but the next topic which is coupled with it, that is the dimension analysis. You will see that if you do not very well understand the phenomena, despite you apply the method, you will not get the required results. So keep this in mind, because when you solve problems, this will not be given to you that, okay, you consider the Froude number or you consider the Reynolds number or other numbers that we are going to study in the coming slides. So that's you have to identify that for this given problem, for this given case, what dimensionless number you can consider for dynamic similarity. Clear? So this is important. Now we studied about this. So we said that in similitude that we consider between the model and the prototype, so for the Froude number in the model, that should be the same as the Froude number in the prototype. Now we are not saying that the velocities will be exactly the same. The characteristic length must be exactly the same. No, we are saying that whatever the proportion of these variable, it should be such that it gives the same value for the Froude number both in model and the prototype, in which case we can say that there is dynamic similarity between the two. Now one thing is possible. For example, you see here that we have this acceleration due to gravity. So because the model and the prototype both are on the surface of the earth, so in that case subjected to the same acceleration due to gravity, so this can cancel out. But if, for example, the model is on the surface of a moon and the prototype is on the surface of earth, then in that case this g cannot cancel out, because the acceleration due to gravity, that is not exactly the same. So we have to take care of these things. Now, as I said that for a problem, when we consider the dynamic similarity, then we need to develop what is known as the scale ratios. And this is actually also a topic in this chapter because this is very important. We call it as scale ratios. And these scale ratios that we can write down or develop for these different dimensionless numbers, for different physical quantities, these can actually help us to quickly analyze the problems. In problems, these will help. Otherwise, you have to first develop them and then you have to put the values and then you have to analyze the problem. So this is very important. You should understand these scale ratios. And these scale ratios are nothing. For example, we already studied some of them. For example, we have LR, which is the length scale ratio. So this is actually equal to length of the prototype divided by the length of the model. This is the length scale ratio. Now, as I told you before, in some fluid mechanics books, you might find that instead of LP by LM, it will be written as LM divided by LP. So this is also possible. And this should not make any problem in the solution, in the question, in the analysis. So this is actually, we denote by lambda in our textbook, and this is known as the model ratio. Clear? This is known as the model scale or model ratio. Clear? So you use this one when you solve a problem, or you use this one when you solve a problem. It should not make a mistake. But anyhow, we will follow this one as per our textbook. So this is what concept we are going to follow. But if you follow this thing, it should not be a problem. Okay. Now the scale ratios that we discuss, so we can develop these scale ratios for these different dimensionless numbers. We can develop the scale ratio for Reynolds number similarity. We can develop these scale ratios for Froude number similarity. So let us discuss a few scale ratio for Froude number so you can realize how they are developed. And then a full table is available in your textbook where they develop for the different characteristics. For example, you consider geometric, maybe length, area, volume. You consider kinematic, maybe the time, velocity, acceleration, discharge. You consider, for example, dynamics. So in that case, mass, force, pressure, impulse, momentum, energy, work, power, because you have to transfer the results between the model and the prototype. So that's why these scale ratios you will require. They can easily. For example, if you know what is the length LR, this is the scale ratio. Remember, when you see a subscript R, it means that this is the scale ratio. So if you know the scale ratio, what is the advantage? The advantage is you multiply with LM, you can find the corresponding length in the prototype. Or if the length in the prototype is given, you divide by LR, you can calculate the corresponding length in the model. So that is the same case. For example, if the power in the model is this much, what will be the corresponding power generated in a prototype? So that you can easily convert if you know the scale ratio, the power scale ratio. So that's why this is very important, the scale ratios. So how we develop them, let us try to discuss in the context of Froude number. But you can develop in a similar fashion for any number given to you considering this similarity. So for example, we know that this V, it varies as square root of G and characteristic length L. So now the velocity scale ratio, VR, this is the velocity scale ratio, VR, this can be written as Vp, velocity in the prototype, divided by Vm. This can be written like this. Now from here you see that this can be written as square root of LR divided by 1. This 1 is that because this G cancel out. We are assuming that this G cancel out. So you can see here from this equation, if you compare these two, you will get that relationship. Clear? So this will be equal to, this is Vp by Vm. Clear? So from here you can obtain, and this will be for the same, this will be for the remember, this is important, for the same F and G. For the same F and G. So we get this relationship. Clear? You see this Vm will come here, this Lp will go here. So this is the scale ratio. So it means that if you know the length scale ratio, you simply take square root of it. The model and the prototype are both subject to the same acceleration due to gravity. So this will be equal to your velocity scale ratio, Vr. This is the velocity scale ratio Vr. And once we can calculate Vr, you, for example, multiply with Vm, you can calculate the velocity in the prototype. You can see the advantage of these scale ratios. For example, let us consider Tr. We consider the time scale ratio. So Tr, this will be equal to time in the prototype divided by time in the model. Now, for example, you estimate the time for any fluid flow in model, and you want to calculate that what will be the corresponding time in the prototype. So for that, if you are able to calculate the time scale ratio that you can multiply with the time in the model, you can estimate the time in the prototype. That's why these scale ratios are important. When we solve the problem, you will further see the importance of these scale ratios. So now this TR, we already know that this can be written as LR. This can be written as LR divided by VR, because we already know that S is equal to VT. We already studied before that S is equal to VT. So from here we can write down this LR divided by VR. Remember, whenever you see R, it means that it is P by M for that quantity. So now LR is LR and VR, this is already written here, square root of LR. So that's why this can also be written as LR divided by 1, because this is for the same F and G. This is for the same F and G. You see, in case of the Froude number similarity, the scale ratio for velocity is the same as that for the time. Now how this comes, this is easy, you can easily do it. You see, this is LR, so this LR is what? This is, let me do it here. We see you have LR, length scale ratio, divided by VR. So VR is square root of LR. So this is square root of LR. Now this can be written as the numerator as square root of LR into square root of LR and divided by square root of LR. So we can see this cancel out and we are left with this LR. which is written here. Clear? For example, you consider acceleration, you want to calculate the scale ratio for acceleration when we have Froude number similarity. So we already know that acceleration can be written as velocity by time. So we have VR divided by time scale ratio. So now you see these two are same. So that's why the acceleration scale ratio is 1. It means that the acceleration for Froude number similarity will be the same in the model and in the prototype. Clear? This is for the same F and G. For example, you want to find out the scale ratio for the discharge. Because you have Froude number, you want to calculate that if the discharge in the model is this much, what will be the corresponding discharge in the prototype. So this QR, that will be equal to QP divided by QM. Now we already know that Q is equal to A into the velocity. So this will be equal to LR 5 by 2 divided by 1, because we consider G as the same in the model and the prototype. Now how this ratio is 5 by 2, you can easily prove this. Clear? This Q, that is equal to area into the velocity. Now for area, what is the scale ratio? That is LR square. And for velocity, what is that? That will be equal to square root of LR. So if you simplify, you will get this LR 5 by 2. Now this is the case when we have complete similarity between the model and the prototype. So as we already studied, that sometimes what can happen is that maybe we have not complete geometric similarity, as in case of river model. For example, we talk about the river model. So we already discussed that in case of the river model, maybe we can use a distorted model. Clear? Distorted model means that the geometric similarity is not satisfied in all the dimensions. When we have river model, well then in that case, if you remember, what will happen? For the Froude number, we find that, you see, for river models, we usually need to use an enlarged vertical scale to provide the model with adequate depth. Clear? So you see, we often use enlarged vertical scales in models of large water bodies such as lakes, reservoirs, etc. Clear? So now in that case, what will happen is that this V, it will vary. This will V varies as square root of LR prime. So you see, we have LR, this is the length scale ratio, and then we have LR prime. You remember from there, this shows that the two scales are not the same. So then in that case, in a river model, V will vary as square root of LR prime, where LR prime is the length scale ratio in the vertical direction. So then in this case, if you want to calculate this QR, so that will be equal to QP divided by QM. And because velocity is LR prime, so that's why it will be LR. One LR is coming from the area and another LR prime into square root of LR prime. So this will be equal to LR prime 3 by 2. Why? Because your area is this one. Area that will be equal to LR into LR prime. So that's why LR prime square root into LR prime will become 3 by 2, and we have LR. So then in that case, this will be the scale ratio that we will use for the discharge in case of distorted models, such as that we have in case of river model. So these are a few examples. You can see here that these are the scale ratios that we develop for the Froude number. You can develop for these parameters and more parameters for Reynolds number and other numbers that we are going to study. So for Reynolds number, there is a solved example in your textbook where they have developed these scale ratios. But in case of Froude number, we develop them here as an exercise that how we can develop these scale ratios for these different physical characteristic or quantities. Clear? Now the third one, that is the Mach number. So the Mach number, it is defined as the square root of the ratio of inertia forces to the elastic forces. Clear? So this is the Mach number. Now remember, all the dimensionless numbers, they are denoted by the bold face letter, capital letter. Clear? Reynolds number, capital bold capital R. Froude number, bold capital F. And now the Mach number. Now you see that in this chapter we will discuss a few dimensionless numbers that are more commonly used. Now in our case, what we have studied so far is that we have extensively used the Reynolds number and we have extensively used the Froude number. Reynolds number we studied in case of pipe flows in fluid mechanics 2 course, and in open channel hydraulics we extensively studied about the Froude number that we considered and analyzed the problems. But these other numbers are also given in your textbook, because if we study about the compressible fluids, then in that case we have to use these dimensionless numbers for dynamic similarity. So remember, these are for understanding and introduction, that it is not just that we have only Reynolds number and Froude number. You have to identify that what forces, because we already studied in the previous lecture, there can be other forces present in fluid flow, fluid phenomena. So that's why correspondingly we define these dimensionless numbers. Clear?
Excuse me, sir.
Yes, what is the question?
सर ये जो हमने होल स्क्वायर लिया, ये मैक नंबर पे स्क्वायर नहीं आएगा?
No, the Mach number is a pure number. When you get the value from here, that is a number. Then there will be a confusion that, for example, we take it also here. If I go back, so here we also take the square root. You see, this square root results into this number. If, for example, you say that, okay, I write down this f as a square root, then there will be a confusion. Then in the problem you will calculate this f. For example, if f is given, so you will say that no, Froude number is square root of this f. So then there will be a chance you make a mistake here, you see. So that's why it is from here the square root of the forces, which is already simplified into this here. So that's why here we do not say that we should take square root of this number. Is it clear now?
Yes, sir.
Okay. Now we have this Mach number, which is the ratio of the two forces, inertia force by elastic forces. To take the square root, we get this expression here. So V is the velocity and C is the sonic velocity. Clear? Velocity of the sound in the medium in question. So the Mach number is the ratio of the fluid velocity or the velocity of the body through a stationary fluid, so to that of a sound wave in the same medium. So this, you remember this C, we already calculated square root of EV by rho. You remember water hammer in the previous course, we actually developed this equation and I derived this equation for you. This EV is the volume modulus of elasticity and rho is the density of the fluid. So when we consider compressibility of the fluids, for example, we studied about the water hammer. Also, we can study about the compressible fluids, but actually that chapter is not part of your syllabus. So, and then in that case, we have to consider this Mach number. You see that because of the compressibility of the fluid, when you suddenly solve, it is compressed. As a result of that, a pressure wave was generated and then it travels upstream. And with what velocity it will travel? It will travel with this velocity c. So the cases where compressibility of fluid, that is important, we have to consider the Mach number. Now if you further go into the depth, just like we say the Reynolds number, more than, for example, in pipe flow, more than 2000, we say the flow to be turbulent, less than 2000, it is laminar. For example, in Froude number, we say if it is equal to 1, we have critical flow. More than 1, velocity is more, so that's why we have supercritical flow. Less than 1, the depth is more, so that's why we expect the flow to be subcritical. Same is the criteria here. So if, for example, you see that the Mach number you calculate, if it is less than 1, we say the flow is subsonic. If the Mach number is equal to 1, the flow is sonic. If it is greater than 1, the flow is supersonic. And if M is extremely high, it can be called as hypersonic. Now, how to determine this, to classify what is subsonic, supersonic, sonic, hypersonic? This has to do with the speed of sound. We can study this in detail. But because these things are not included in your syllabus, so that's why we will not go into detail of these things. You see, Reynolds number we studied in detail. Froude number we studied in detail. If we have a chapter on compressible fluids, then in that case we will study this Mach number in detail. Clear? So there we can determine that what we mean by sonic, subsonic, supersonic, hypersonic. Clear? Also, the Mach number, if you square this number, we get another number that is known as the Cauchy number. If you square this number, you calculate this M and you square it, this expression, so we get another number that is known as Cauchy number. So remember, now onward, this discussion is just for introduction. Because we do not study in detail the theory related to these, so that's why, because of the limited time, and since these are not part of our syllabus, we will not study them in detail. But given here to tell us that it's not only Reynolds number and Froude number. In any fluid phenomena, for dynamic similarity, you have to determine that what forces are significant, and accordingly we can determine that what dimensionless number is important. So as I said that in case of compressible fluids, this Mach number is very important. Let us see a small video to identify the case where we can say that this is important. Now you can see here that in this case, this is a wind tunnel. You can see the facility. This is a wind tunnel, and in this wind tunnel, in this example, this model of an aeroplane that is placed. Now the air will flow past this model of the aeroplane, and in this case the fluid cannot be considered as incompressible, because you can see that the speed with which these fighter jets or aeroplanes they fly, then in that case we can no longer hold the assumption that the air, it will be treated as incompressible. So this is an example where if you study these type of model studies, so then in that case, we have to consider these Mach number for dynamic similarity between the model and the prototype. Clear? Now the next one is the Weber number. So the Weber number, it is defined as the square root of the ratio of inertia forces to the surface tension. So now in any fluid phenomena where you feel and you understand that the surface tension is the important, then in that case between the model and the prototype for dynamic similarity you have to consider the Weber number. And you already studied surface tension in detail in your fluid mechanics 1 course, that surface tension, this is actually the it occurs at the interface between the two different fluids. For example, it occurs at the water surface. So at the water surface, it is the interface between the two fluid, water and the air. So that you have to identify that in which cases this surface tension, this becomes important. So accordingly, then we can consider the Weber number. Now I said before that by studying these numbers, it does not mean that in every fluid mechanics you have to consider all these numbers at the same time. You have to see that which forces are significant in the specific given fluid mechanics problem phenomena, and then accordingly for dynamic similarity you have to consider these dimensionless numbers. It does not mean that you have to consider all of them in the same problem. Now this Weber number, if you put the expressions for the inertia force and the surface tension, so then in that case we get this expression here. Clear? Now this Weber number, it is named after this Weber because Weber, he developed initially the modern laws of similitude. Now one thing is important to mention here is that, for example, we defined the Reynolds number. So it may happen that the Reynolds number was not defined by the Reynolds himself. He just conducted that very famous experiment to visually observe the laminar and turbulent flow by using a dye color that was injected into the flowing stream. It can happen that later on we develop the ratio of inertia force to the viscous force, and it was termed as the Reynolds number to honor his contribution. Similarly, you can see here this number, it is named after Weber because he initially developed the laws of similitude that we use today in the model studies. So remember, it's not always the case that specifically that person give us this number. It may happen that the person help contribute in any understanding of the fluid phenomena, and later on we name the units and these dimensionless numbers after them to honor them. Clear? For example, the force unit is Newton. So maybe during that time when Newton was there, he did not say that, okay, take the unit of the force as Newton, but later on, just in recognition of his contribution, we name the unit as Newton or Pascal for pressure, etc. Now an example of an application of the Weber number is at the leading edge of very thin sheet of liquid flowing over the surface. If you study this fluid problem, then in this case we have to consider this Weber number because then surface tension effects will be significant. Clear? For example, I show you in this video. So you can see that in this case here, this is a bubble. So at the interface, so you can see that here the surface tension effects that are significant. So in study of such cases, then we have to consider this Weber number as the significant dimensionless number for dynamic similarity. The next one is the Euler number. Now, Euler number, what is this? It is the ratio of inertia forces to the pressure forces. If pressure forces are significant in any fluid phenomena, then we have to consider the Euler number for dynamic similarity. Clear? Now, because the pressure forces, they can be written in a variety of ways. Clear? So that's why you see that it can be expressed in a variety of ways. One form being is this one. So inertia force by the pressure force. So this is equal to this expression which is given in your textbook. But maybe this Euler number you find in another fluid mechanics book, and maybe the expression is slightly different. So you are confused which one is correct. That's why it is written here that it can be expressed in a variety of ways. One form is this. Clear? So you see that Euler, he is actually famous for his contribution in pure mathematics. Clear? But you can see that the concepts that he developed today, even we apply and analyze the problems in different engineering areas. But you see, Euler, he was a pure mathematician. So we name this number after him to honor his contributions. Clear? So this is known as Euler number. So if only pressure and inertia influence a flow, the Euler number for any boundary form will remain constant. Means that for dynamic similarity, the Euler number should be the same in the model and the prototype. So you can see here that gamma is present here, you see, for this form. So if other parameters such as viscosity, gravity, G is present here, you see, and you see gamma here or rho here. So if other parameters cause the flow pattern to change, however, E will also change. Now, these are the numbers that are explained in your textbook, these number, and in addition, we have some other dimensionless numbers. For example, if we rearrange the Euler number to evaluate 1 by E square now, we get a dimensionless quantity known as the pressure coefficient. So the pressure coefficient, this is equal to this change in pressure divided by half rho V square. And if you remember this half rho V square, we studied in detail, and I actually proved this for you also in case of I taught you that time, if you remember in fluid mechanics too, that this is actually the dynamic pressure, this half rho V square. And actually I developed this using the Bernoulli equation. Clear that how we define this dynamic pressure. You remember the total pressure, the static pressure, and the dynamic pressure. So that's why you see that this is known as the pressure coefficient, other dimensionless number. Clear? Now in this, if this delta P, if this is referred to the vapor pressure, see, that's why we say if this is referred to the vapor pressure, that's why I say that this can be written in different forms. One form is this one. So now if we refer this delta P to vapor pressure, the pressure coefficient becomes a dimensionless quantity called the cavitation number. This is known as the cavitation number. You see now delta P we write down in this form, P minus PV. Here both the pressure must be the absolute pressures. Clear? So this is then known as cavitation number, another dimensionless number. Clear? Now, maybe in some books, you see that some authors, maybe they do not write this 1 by 2. They omit this 1 by 2 from the definition. But anyhow, this is what is written in your textbook. So let us proceed with this one. So now 5 numbers we studied before. These are the 2 numbers. You see that the 7 numbers, dimensionless numbers, that we just studied are among the best known and most used. Some others that we also studied without thinking about them. For example, specific heat ratio you might have studied in your mechanical technology course, although we do not study compressible fluids. Similarly, the friction factor, you remember, it is a dimensionless number. We studied extensively in the pipe flow chapter. And the lift and the drag coefficient that we studied, these are also dimensionless numbers. And remember, if you study a book, the name is Handbook of Fluid Dynamics by Johnson. There, the author explained more than 150 dimensionless numbers. More than 150 dimensionless numbers. So that's why when you consider any fluid phenomena, you have to identify what forces are significant, and then accordingly that dimensionless numbers that you have to consider for dynamic similarity. So if you study that book by Johnson, Handbook of Fluid Dynamics, there you will see they explain more than 150 dimensionless numbers. So here what was given in your textbook, that is actually an introduction to this similitude. Clear? Now we discuss the scale ratios. As I said, that this is very important when we solve the problems. So these scale ratios are actually given in the form of a table for these dimensionless numbers. You can see here we have the characteristic, and if we consider geometry, then in that case you have length, area, and volume. Now the scale ratios, they are developed for the Reynolds number, for the Froude number, and for the Mach number, because the textbook says that these are the most commonly used in fluid mechanics. But you can develop these scale ratios for other dimensionless numbers also. We are mostly concerned because we studied Reynolds number in detail and we studied Froude number in detail. So you can see, if you consider kinematic, then for the time, for the velocity, for the acceleration, you see that these are the scale ratios. If you consider the Reynolds number for dynamic similarity, these are the scale ratios. You see that this we just developed. You see, for the time, what we developed, that it is square root of LR. You see R is written. Whenever you see R is written in a subscript, remember it means that it is the scale ratio. When you have LR, clear, when we have LR, so it means that this is LP by LM. Whenever you see the scale ratio, so it actually means LP by LM. So now these quantities are written. So actually this means that we have L square. This is for the Reynolds number similarity. We have rho and we have mu. This is for the prototype, divided by L square rho and mu for the model. So you see, when R is written, it means that it is the scale ratio. Clear? You see, for the time, considering the Froude number, we already developed this. Clear? For acceleration, it was 1. So you see, it is written GR. It means that it is acceleration due to gravity in the prototype divided by acceleration due to gravity in the model. If both are on the surface of the earth, this will be equal to 1. This is what we already discussed. You see here, this is what we discussed. These are given in your textbook here. You see AR, it was equal to 1. For the same G, both are on the surface of the earth, so it is equal to 1. You see, for the time, it was equal to square root of LR. This is what is given in this table. When we solve the problems, then actually these scale ratios can quickly help us to analyze the problem. Otherwise, first you have to develop these equations and then you use to solve the problems. So that's why in your textbook, actually this is given in the form of a table. And they are directly calculated for, developed for these three numbers. But you can develop the same for other dimensionless numbers also. And the table continues. You see here we have discharge. And if you consider the dynamic, you see we have geometric, then we have kinematic, and then we have the dynamic. So you see we have the mass, the force, pressure, impulse, momentum, work, energy, and power. So you see that these scale ratios you can directly use when, for example, it is given in the problem that you consider the similarity of the Reynolds number, and if the power developed in the model is this much, what will be the power developed in the prototype? You can use this here. So that's why remember that these scale ratios, these are very helpful when we analyze the problems. Clear? Now we try to wind up this similitude. The next part of this chapter would be dimension analysis. We can continue and discuss more and more in detail, but anyhow, due to the time constraint and also as per our textbook, so this much will be sufficient. Now, when using models, the fluid velocity should never be so slow that the flow is laminar when the flow in the prototype is turbulent. Now these comments on models are actually mean to tell us that the concept is not that easy to apply. That okay, now we say that the Reynolds number should be the same and just make it the same in the model and prototype and just solve the problem. You see, we can face some challenges, some issues in the model studies. We have to be very careful when we transfer the results from the model to the prototype. For example, in this case, it says that when using models, the fluid velocity should never be so slow that the flow in the model becomes laminar flow, where in the prototype we have turbulent flow. So we already studied in detail that laminar flow and turbulent flow, these are two different flow regimes. They have different characteristics. So that's why if in the model you have laminar flow and in the prototype we have turbulent flow, we cannot effectively transfer the results. So this we have to take care. Similarly, conditions in the model should not allow surface tension to be important if it is not in the prototype. For example, the depth of water flowing over the crust of model spillway should not be too small. When we conduct the model test on a spillway, we have to make sure that the depth on the crust of the model spillway is not too small, because in that case surface tension effect will be significant, which may not be the case in prototype. If we have to ensure these issues, these are appropriately addressed, only then the results that we transfer from the model to the prototype, or we predict the performance of the prototype from the model, only then it will be effective. Now, what we say is that proper judgment should be used in transferring the model results to the prototype. I will give you one more example on this. There can be one or two more examples. You study your textbook. So it is not always necessary or desirable to adhere to various dimensionless ratios in every case. See, thus in the tests of model centrifugal pumps, geometric similarity is essential, but we need to operate them at such rotative speeds and all fluid velocities are same as in prototype. What it says, that it is not always necessary to adhere to these dimensionless ratios in every case. We studied about the pumps. So it says that, okay, you ensure geometric similarity. That is essential. As I told you before, you cannot conduct test on a car and transfer the results to aeroplane. So geometric similarity is essential, but in case of centrifugal pump, we have to operate at the velocities must be the same as in prototype, because this is the only way we can detect cavitation. This is what is written in your textbook. What it means, you see cavitation, I already give you some introduction in pumps and turbines in the previous course. We studied that. I told you that, for example, let me give an example here to further highlight. Let's say we have a pump and this cavitation we have to avoid. This cavitation we have to avoid in case of pumps and turbines, because it can occur in hydraulic machinery. So this we have to avoid because it can damage the machine, pump or turbine. So when we design or we operate these, we have to make sure that cavitation does not occur. So what is cavitation? As I told you before, that cavitation is that because the fluid passes through these machines and there is increase and decrease in pressure, so the pressure, it should not fall below so much low that it is the temperature falls below the boiling point. Clear? It means that if the fluid boils, because you see the boiling point of water, it is 100 degrees, but it is not fixed. This 100 degrees centigrade is under atmospheric pressure. If you decrease the pressure, the boiling point of water will drop. So water can boil at lower temperature. If you increase the pressure, so the boiling point will also increase. But if you decrease the pressure, you already studied this in your school, college physics. So if the pressure is very small, then the water will boil at much less temperature. So what happened is that you see that in case of this pump here, let me explain from this example what I'm saying. Let's say if you want to pump the water from a lower level, so you see here that the pressure will be minimum on this side. That's why you see that this is suction side. Clear? This is suction side, suction pipe. So that's why we have low pressure here, low pressure on this side. Let me explain from this example, it will be clear what I want to say. We have low pressure, and then from this side, because pump aids the energy, so that's why from here this water and it goes to, let's say, a reservoir, no problem, overhead tank. So now on this side you have very high pressure at this side here. So we have high pressure. Now this cavitation is, we can study in detail that why it occurs. There are several reasons for that, but whatever the reason is, what happens, that I explain to you in this short time. So what happen here is that when we have low pressure, so this low pressure should not drop below the vapor pressure, because in that case the water will boil. Clear? So what will happen is that when the pressure becomes so low in this suction side, so you see here it is minimum before the water enters, moves over the blades, clear, of this pump runner, which we call it as runner, vanes, blades, that we already studied. So what will happen is that cavities will form, because when the water boils, what will happen? Cavities will form, bubbles will form. So these bubbles, when they pass over these runner blades, so what happens is that they move from low pressure to high pressure. They move from low pressure to high pressure. So when they reach here on this side, what happened? Let me draw. Let's say we have this metal surface. This can be the blade of this runner, and it can be even the pipe on this side here. So what happened is that this bubble, it stick to this surface here. This is now the bubble. Now this bubble, what will happen? Because this bubble develop here in the low pressure due to boiling of the fluid, now this bubble moves to the very high zone. So this bubble will collapse, because now it moves to the high pressure zone, it will collapse. So when it collapses, what will happen? The fluid from all direction, because it is a bubble, when it collapses, the high pressure fluid, it will move with very high pressure from all directions. And when it comes here, you see enormous impact will be developed here. And if this is the metal surface, then what will happen? It will try to put so much pressure here that it will eat the material from here. And as a result, a very small cavity will be created here. And if this process continue, another small cavity will create, another small cavity will create, and you can see it will cause damage to the runner of the pump turbine, and also even if this occurs here. So that's why this cavitation is very dangerous. We have to avoid this, and we can ensure this. When you do the analysis, actually we have the net positive suction head. Net, actually this we need to study in detail, but net positive suction head. So we have this net positive suction head. This is, we have to calculate. One is the available and one is the required. That is given by the manufacturer of this pump. That is the net positive suction head that is required. That is required. So we have to make sure that when we select the proper pump, and also we place it in such, we operate it in such a manner that this available net positive suction head is always greater than the net positive suction head required. So in that case, we can avoid this cavitation. So because you see here, I think show you picture maybe into your textbook available. It is so enormous, it can even eat away the material. That is known as pitting. If we have the metal surface, it will try to eat the material because of this high impact. And this is known as pitting. Clear? And you see, if it continues, you see on the surface, these small cavities will be created, the material is removed. That's why it is known as cavitation. So just to wind up the discussion here, it is stated that in order to detect the cavitation, so we have to operate the model such rotative speeds that all fluid velocities are the same as in prototype. because this is the only way we can detect the cavitation. So it means that model studies, when we conduct the studies and we try to predict the performance of the prototype from the model studies, we have to address all these issues. It's not that simple, just develop model, whatever the results you get, and then you try to predict the performance of the prototype. So it's very conceptual topics, clear that you must be very much clear about the fluid phenomena in order to interpret the results. One last example to show here, this is the picture which is given in your textbook. Now this is, you can see that it is the model of a bay, clear. So you see that the geometric similarity is not 100% achieved. You can see LR is 1000 and LR prime it is 100. So it means that we have a distorted model, as we already discussed in case of the river models, that we have these distorted models. Now this model, it was developed to simulate the behavior of the flows in the prototype. Now to the important point here to discuss is that in the prototype we have the frictional flow resistance, clear, in the prototype. So how we simulate that frictional flow resistance in the model? For this case, what the hydraulic engineers did is that they put vertical metal tabs that were installed in this model. You see the vertical tabs here in the flow, this white one shown here in this black and white picture, to provide proper frictional flow resistance that is similar to the prototype. So now on one side, you try to simulate the behavior in the model to be the same as in the prototype. Only then you can predict the performance of the prototype or get idea that what will be the effect in the prototype. So on one side we did this. Now the next question is how we place these metal tabs, what quantity and what spacing. This is now the issue we have to address. So there is no simple rule for this, clear. Is any distorted model lacks proper similitude? As you can see here, the scales are not the same. Now there is no simple rule for this. We must adjust the roughness by trial until we judge the flow conditions are typical of those in the prototype. So you see what they did is that these metal tabs that they put to simulate the proper frictional resistance by trial and error procedure. Model studies are not that easy. You can now understand one thing. Now you put these metal tabs, we face another issue. What will be the other issue? That these vertical distortion or these disturbs circulation pattern. Now what happen is that these will disturb the circulation pattern. What we mean by this? The metal tabs, that these will create large scale eddies, because when the water flows they will create eddies. So hence we must interpret mixing in distorted models with caution. For example, if you consider here the disposition of pollutants, so because you see these metal tabs, they will create eddies. So then the mixing, the disposition of pollutants, that we have to carefully interpret from this model to that in the prototype. So on one side we try to solve one problem, on the other side it becomes a potential issue. So that's why, remember, these model studies, we need to be very careful and we should understand, only then we can effectively conduct these tests and we can predict or simulate the behavior of the prototype. So before I take a break, I just show you 2-3 videos so that you can further see in the model studies that can help us to understand the prototype behavior. And before that, I just explained this last thing that I already said many times before. You see here that we have this prototype here. This is of a dam, and in here we have the physical model that is developed. So now you see that this we already discussed, that flows with free surfaces present unique challenges in achieving complete dynamic similarity. For hydraulic applications, depth is very small in comparison to horizontal dimensions. If geometric similarity is used, this we already discussed in detail, the model depth would be so small that other issues would arise. For example, what we discussed, that surface tension effects would become important. And then in that case, Weber number you have to consider, otherwise results will be an error. And also this will make the data collection difficult. So what is the solution? That we use distorted models. They are therefore employed, which requires empirical corrections or correlations to extrapolate model data to full scale. You see, it is written here empirical correlations to extrapolate the data. The very common example is the Manning's formula. You see the Manning's formula, that is empirical equation. The Manning's formula, it was developed from the laboratory data. It has no mathematical proof. It just fits the data through regression analysis, and we developed the Manning's formula. And now you see that the Manning formula we are using in the design of open channels, the prototypes. So this is actually what it says here. Let us watch 2-3 videos, then I will take a break. Now in this here, what you see that this is actually a wind tunnel and a full scale, now not a model, a full scale race car that is being tested. And you can see the streamlines that can flow. And here, similar to this, I show you many videos in Fluid Mechanics 2 course when we study forces on immersed bodies. So this is how we can determine the effect of the shape as the fluid passes around this object or full scale car. This is a race car. So this is how we can see the effect, and then we can determine how to reduce the drag forces so that it can travel faster, because it is a sports car. So the idea would be that it can travel faster and faster. Now this is another model you can see here. Now debris or suspended solids are put in the model, and we want to see that how when they flow through this hydraulic structure, you can see here clogging can occur. So how we can improve the design so that this does not happen in the prototype, or at least we can minimize it. Now this is another case. We have the dam, spillway, road, and the downstream we want to simulate the flow pattern. You can see here that from this model study what we can get the idea that what will be the situation in the prototype, and what we can do that if there is any potential problem, that we can improve the design to avoid that problem in the prototype.